All right, folks, so we are going to continue our discussion of electrophoresis as a separation method. There are actually a number of different ways in which the principle of electrophoresis can be applied to separate molecules. We'll get to touching on quite a few of these as this discussion goes on, but we're going to start at my favorite, which is called capillary electrophoresis. And capillary electrophoresis, or for short, because that's a lot to write out, CE. Okay, so let's start this by kind of recapping the two mechanisms that we discussed last time. So electrophoresis is the movement of ions in solution in response. Here, let's make sure there we go, in response to an applied electric field or E field. Right, so we apply some potential difference over some distance, and ions want to move in response to that. The second mechanism we looked at last time was called electroosmosis, or electroosmotic flow, which we abbreviate EOF. And this is the bulk flow of solution in a capillary or some other small confined space with a lot of surface area. We'll say in a capillary. Again, in response to an applied electric field. Okay, so let's put these two concepts together to draw a picture of kind of the fundamental working mechanisms of capillary electrophoresis, or CE. So let's draw a capillary. Here it is. It's the inside of the capillary. Into this capillary, we're going to inject a small plug of sample, just like we would do for HPLC. So here's that small plug of sample. That's an injected plug, and we're going to get to how that happens a little bit later, but for now, just take my word for it. Somewhere down the line, at the end of the capillary, we're going to put some kind of detector to watch things go past. And again, we're going to get to what these detectors are and their properties a little bit later. But the thing I want to talk about right now is what causes separation to happen in this capillary. So we apply voltage, plus V down here, minus V down here. And due to electrophoresis, molecules in this injected sample plug, remember there's a mixture of multiple different molecules, they all want to move, right? They want to move in response to this electric field. So let's draw a couple of different molecules moving at a couple of different velocities. We'll call this velocity sub EP, electrophoretic. We'll call it 1, it's molecule number 1. Here's some other molecule, moves much more slowly. Velocity electrophoretic 2. And something else that also moves pretty fast, velocity electrophoretic 3. But the thing to know about all three of these electrophoretic velocities is they're moving away from plus and towards negative. That means they all have positive charges. All of these velocities belong to cations. And their velocities, let's just put this down here. So the velocity, the electrophoretic velocities of each of these molecules is proportional. We saw this last time to the number of charges over, sorry, I'm going to draw this as a lowercase r. So it's the number of charges of the ion over its hydrodynamic radius. So larger hydrodynamic radii slow these things down, higher charges speed them up. Okay, these are all cations. That must mean then that anions are doing this other thing. They're going in the other direction. So here's VEP, 4? And we'll draw another one. It has a different velocity. We'll call this VEP 5. But the take-home message is these are all anions because they want to go in the other direction. Okay, so we know that this is true. That their velocities are proportional to these, and so therefore, if we're seeing different velocities, what we're saying is that analytes with different Z to R ratios will reach the detector at different times. And that, my friends, is the very basis of separation. Right? In all of our chromatography methods, we made this happen. We got different velocities because of phase transitions or extractions, repeated extractions in liquid chromatography. In this case, it's going to happen by the nature of these molecules and their size to charge, or the charge to size ratio. So this is separation. This is the good stuff. This is what we're after this whole semester, right? It's different velocities of different analytes. Okay, but the way this picture is drawn, it kind of suggests that only our cations are ever going to see our detector, and our anions never will because they're going in the wrong direction. And this is where our good friend electroosmotic flow comes in, and that's because the velocity, actually let's say that this is typically, we're going to see a little bit later when this would not be true, but typically the velocity, V sub EOF, the velocity of electroosmotic flow, is typically quite a bit larger than these electrophoretic velocities. That means if these are all vectors illustrating how fast these things are going, the vector that illustrates electroosmotic flow is much larger, something like that. Of course, they're all moving in bulk together. The net result here is that in most cases, when your electroosmotic velocity is larger than your VEP, and when you don't have particularly huge negative electrophoretic velocities here, we can say in most cases, cations and anions are detected. Okay, that's the basic fundamental working principle of how capillary electrophoresis produces separation. Let's talk a little more specifically about that separation. Let's start by talking about migration order. And you'll notice I'm saying migration order and not retention order. And that's because we use just a slight tweak of the language when we talk about electrophoresis, because there's no retention to speak of. There's no stationary phase retaining this stuff, right? All that's happening is they are migrating through this capillary at different velocities. And so we don't talk about retention time. It's not T sub R. We talk about migration time, T sub N. It's the same, concept for things like resolution, but it gets a slightly different language. So let's talk about that. Let's talk about migration order. And here's the way I like to think about this. So migration order in CE. I like to imagine that all of my analytes are going to start out in some plug like this. So this is a mixture of everything. It's cations, it's anions, it's neutrals, it's everything. And because of this effect that we just talked about, some of these are going to go way out in front of everything else, and some of them are going to go way behind the others, right? So I'm going to draw those out. I'm going to get kind of a feel for how this works. So way out in front here, the fastest stuff is going to be small, or it's going to have a high charge, right? So let's look at that. Something that's slightly larger, but it has 3+ charges. Okay, so it's going to be smaller. It's going to be highly charged. We're going to see our moderate sized. We're going to just normalize all this thing to 1 charge. Let's assume everything has 1 charge in it. Then the bigger it gets, the closer it gets to where it started. Okay, we've also talked about how neutrals all have an electrophoretic mobility of 0. So it doesn't matter the size of these things. None of them are moving any different velocity than just the velocity of that injected plug. Okay, but on the other side of this injected plug, well, it turns out it's the exact opposite trend, right? The stuff that is highly negatively charged but small, so the negative equivalent of this, that's getting way out here, right? There's our small negative thing. Our moderate negative things are in the middle, and our large negative things are back here. And so this becomes our migration order. We're going to say this is detected first, all the way back to detected last, because remember these are moving downstream to some detector down there at the end. So this is the largest value of z over r. It's the largest positive value of z over r, and therefore it has the largest mu sub EP, the largest electrophoretic mobility. This is the largest, hang on one sec here, there we go. This is the largest negative z over r, and therefore let's just really call this what this is. A big negative number is actually a small number, right? A small negative number is a larger number than a big negative number. So this is actually the smallest mu EP. So it goes exactly as we would predict. We just have to remember that the absolute value is not what we're talking about. We're talking about the actual relative size, right? A really large positive number all the way down to a small negative number, all the way down to a big negative number, okay? That's our migration order. We talk about the velocity of these things, not as their electrophoretic velocities. We talk about it as, so let's talk about velocity in CE. We use this term apparent velocity. And that's because we can't separate the two mechanisms, the EOF or the EP. We observe them simultaneously. So instead of being able to talk about electroosmotic velocity or electrophoretic velocity, we say apparent velocity. We call this V sub APP. So that's the velocity we actually observe. If we say we injected at time 0, we saw the peak come out at time whatever. We know how long the capillary was. We know its velocity. That's its apparent velocity. The apparent velocity is just the sum of the EP plus that EOF. I'll remind you, EOF is happening to all solution in the capillary. So every single one of these share the same velocity EOF. They differ just in their velocity EP, electrophoretic. So that is, you'll remember that velocity, we talked about this in a couple different forms, velocity equals mobility times electric field. Okay, so we can talk about, instead of apparent velocity, we can talk about apparent mobility. And that, very simply, is the electrophoretic mobility plus the EOF mobility. And these are terms that we talked about in the last lecture. And so we can say that the apparent velocity is equal to the apparent mobility times the applied electric field. Okay, we're going to come back to this, but before we do, I want us to think about Van Deemter. Okay, so I'm going to just draw, let's see where I can fit this in. Let's draw a separate section over here. Let's consider Van Deemter in CE. So our three terms for Van Deemter are the A term, eddy diffusion, right? That's different flow paths around a packed bed. The B term, longitudinal diffusion, that's just the band broadening that happens over time as a plug diffuses longitudinally on the capillary. And resistance to mass transfer, this is related to the amount of time it takes for things to partition from one phase to the other, right? So there is no A term. Let's start with this. So CE has no A term. And that's because these are open tubular capillaries, right? So these are just open tubes. There aren't multiple flow paths around packing. There is no A term. But here's where it gets super awesome. CE also has no C term. There is no mass transfer to speak of. These things don't take a finite amount of time to transfer between stationary phase and mobile phase because there is no stationary phase, right? There is a B term, but that means that the Van Deemter curve for CE looks like that, right? Here's our B term, and that's all she wrote, folks. That's everything that Van Deemter has to say about CE. So CE only has a B term. And that makes for something extremely interesting. So remember, we should label these axes. This is our height equivalent to a theoretical plate. This is our velocity of flow. And if there's only a B term and we want to minimize this, basically the solution is very simple, right? So with only a B term, faster the better, my friends. Right? You want to make this thing go as fast as possible. You want to maximize apparent velocity, and you do that. Obviously, this is physical constants given to you by your analytes, but that's under your control, right? So you maximize the velocity this thing gets through the capillary to maximize your peak efficiency. And guess what? It's like the win-win situation, right? When we talked about classic Van Deemter, we said, a classic Van Deemter curve for some kind of chromatography method has some minima, right? So this is for chromatography. Classic Van Deemter curve has some minima. We said you never work on this side because you're getting worse peak efficiency and you're taking longer to do it. But you very often work on this side because although your efficiency goes away, at least you're getting your analysis done faster. Well, here's the beauty of CE. You go faster and it gets better, right? CE is like the win-win. It's one of the reasons why I love it so much. So we want to go much faster. That means these E values, these applied electric fields, are typically very high. So E is typically quite large. Certainly larger than about 500 volts per centimeter, but easily getting into the thousands of volts per centimeter. So we're not talking about applying a few volts to make this happen. We're talking about applying thousands and thousands and thousands of volts. The standard would be somewhere on the order of 30,000 volts to make something like this happen. Okay, there's a consequence to that. There is a consequence to applying all that voltage. So it turns out B term, it's the only Van Deemter term that contributes to band broadening, but it's not, so B term is not the only mechanism causing, it's not the only mechanism of band broadening. Whoa, there we go, running out of page, but there we go. It's not the only mechanism of band broadening. And that's because high E fields cause heat. And heat is bad. So heat will produce what we'll call thermal convective currents. That is the actual, so if we picture flow going down a capillary, if there's a distribution, so if we have like a delta T, a distribution of temperatures across like this, what we actually get are different viscosities. We'll have one viscosity up here, we'll have a different viscosity here, and presuming you have a different temperature here, we'll get a different viscosity here. Those are supposed to be etas, not n's. And these different viscosities responding to a pressure field that move them, it's going to cause basically mixing. It's going to cause vortices to cause this stuff to kind of swirl and mix. So that's a thermal convective current. Mixing is always bad, right? Mixing is a mechanism by which something that would have been a nice tight band becomes a very broad band, hence band broadening. So there's a solution to this. So the solution to heat buildup is small diameter capillaries. And the reason for this, we've talked about this one time, at least one time before this semester. It's that as dimensions go down, the surface area to volume ratio goes way up. And that means more efficient heat dissipation. Right, so when we have a lot of surface area, we can pull more heat out of that solution. We can maintain a much more stable temperature as the high electric field puts out thermal energy. We can remove that thermal energy faster than it can be converted into an increased temperature in the solution. So this solution is the thing that causes this to be called capillary electrophoresis. So electrophoresis long predates capillary electrophoresis. But this solution allowed us to get to these really, really high electric fields. And we said the faster the better. And so this really was a revolution in electric field mediated separations. This was invented by Jorgensen. We've heard about him before. Jim Jorgensen at UNC is the guy who got to, a million theoretical plates doing some really, really, really small particle HPLC. He also happened to invent the entire field of capillary electrophoresis in 1981. He's also, I'm just going to brag about this. I always do when I get the chance. He's also my PhD, great-grandfather, my advisor's advisor's advisor. So Jim Jorgensen invented this in 1981. Here's the paper if you want to read it. I'm going to give you this reference just because it turns out my research group is actually, this is part of our journal club right now. We're reading this exact article, so why not pass it along to you guys? This was Analytical Chemistry. It was 1981, which is, volume 53. And the page numbers are 1298 to 1302. So that's where capillary electrophoresis was invented. It was a real sea change in the world of electrophoresis. Electrophoresis was kind of a middling technique that couldn't possibly compare with chromatography until this exact moment when in many fields it far, far, far surpassed chromatography. So we said that heat is a bad thing. Here's a solution to it. What we need is some kind of tool to be able to tell when heat is becoming a problem. Because even with this, with small capillaries, we can't dissipate heat infinitely, right? There's some point at which we're producing too much heat. And so the solution to this is something called an Ohm's law plot. And so Ohm's law, there we go, law, is that we've seen this before, voltage equals current times resistance in a circuit. And that's a nice linear relationship. That's a linear relationship. And so if we take some capillary, we fill it with some solution we want to do a separation in, and we apply various voltages and measure the amount of electrical current produced by that circuit, it should give us a nice linear relationship. So let's plot that. Here's voltage. We're going to change voltage over time. We're going to measure the current that is produced, again, in a system like this, a capillary, where there's a voltage applied here and here, and we're measuring how much electrical current runs through. We should get a nice linear relationship until eventually, at some point, we won't anymore. Right? So this is linear, and this is not. Right? Okay, so Two things I want to do here. The first thing is I want to tell you why this happens, and the second thing I want to tell you is is to point out a massive error in language and the way people talk about this that drives me freaking nuts, that I'm happy to be able to clear up by sharing with you guys. So first thing, why does this go nonlinear? So what's happening is the solution inside your capillary has some resistance, and that resistance is a function of many electrical properties. One of those properties, for example, is viscosity. As the viscosity goes down, ions can move more freely. That gives it a lower resistance. Okay, when it heats up, those properties, like viscosity, change. And so what you have here in the linear range is one value, the same value for R. So you get the same slope everywhere. Once you start producing enough heat that you change those properties, like viscosity, well, then you no longer have the same resistance at this voltage as you do, say, at this voltage. And so you don't get a linear relationship there. You start to go nonlinear. So it's a fairly straightforward concept. The trend goes nonlinear when heating occurs in the solution. But the thing I want to point out to you, it's just something, like I said, drives me absolutely nuts, is people say, well, we measure this until it stops following Ohm's law. And it kills me, man. It drives me nuts. And let me tell you why it drives me nuts. It drives me nuts because Ohm's law isn't called Ohm's strongly worded suggestion, right? It's called Ohm's law. Nothing ever stops following a law, right? What happens is the properties of your system change. It continues to follow this law of nature. It just happens to no longer have the properties you thought it did back here. So I know it sounds nitpicky, but it's something we should keep mindful of if we find ourselves working in this area. Okay, these are some principles of capillary electrophoresis. We are going to keep talking about some neat properties that some of these mechanisms like electroosmotic flow offer to these separations in the next part of the lecture.